what did we do last time? We were looking at SU3, right? SU3 representations. Okay, we looked at some of the simple representations and also discussed a little bit about tensor products, no? Using I didn't go into too much detail on the tensor products, but maybe we should then proceed. Unless you have some questions on the last time.
I have a question.
Yeah.
When we prove that something for an element group, it's true for elements.
Something what?
Something is true for an element group near to identity using the properties of the algebra.
Infinitesimal.
How we can prove that it's true for any general element? How, like, which is far from
what is true? What is true?
Because, like today, we were doing this representation of Lorentz group using gamma matrices.
Yes.
And then we show that if we have, what did we show? That we have this kind of representation of elements of the Lorentz group using
exponentiation.
Yes.
If we have infinitesimal translation.
Exponentiate these generators. Yeah.
So then to show that the gamma matrix transforms as 4 vectors. And we did only for infinitesimal transformation of an element of this.
Yes.
So then we generalize it's true for any element.
Yeah, it's always exponential math.
Yes.
You just take any Lie algebra element, exponentiate it, and that will give you a finite group element.
So if we show for the first approximation on the parameters, then it's true for any order of for the infinitesimal.
Yeah.
It's always true. If we show something for an element near to the identity, then it's true for any element.
I mean, so what is the definition of the group element, right?
Yeah.
A group is defined, for example, from unitary matrix, right? Now, exponential of a Hermitian, take SUN, unitary matrix. Unitary and SUN means determinant is equal to 1. Exponential of any I times a Hermitian is by definition unitary matrix, right? So it is you're proving it anyway, right?
Okay.
This is just an example. Or take an orthogonal group. Exponential of a antisymmetric matrix is going to be orthogonal matrix. Yes.
Okay.
And the tracelessness condition, the determinant condition we impose on the from the tracelessness, no? So the two things agree then.
Okay.
So you're doing this now, okay. Yeah.
We never did
Yes.
the algebra example non-compact parameters.
I did. I wanted to know.
Are all the discussions up to now also valid for the non-compact?
At the level of Lie algebra because anyway now we are discussing the complexified Lie algebra. So it doesn't matter. No? Take an example. In fact, I will talk about it towards. I want to talk a little bit about spinor representations of orthogonal groups. Maybe the last lecture, if I can finish everything before that. For example, when Eddie discussed this gamma matrices, he wrote down the gamma matrices, right? Which are 4 by 4. Yes. But did he explain why it's 4 by 4? Why it couldn't be smaller? Why it couldn't be, Did he explain that? Huh? Yeah, the similar discussion can be made for any dimension. Okay. So this is what I wanted to just say towards the end. Spinor representations of any orthogonal group. So you were asking about the non-compact version. If you just take, let's say already the thing that we looked at, SU2. For SU2, we had sigma 3 and what we call sigma plus and sigma minus, right? So these matrices were explicitly 1, -1, 0, 0, 0, 1, 0, 0, and 0, 1, 0, 0. Right? So,
before that, we already began with the complexified.
Exactly.
But we also said that with a certain kind of linear combination, we again end up at the
Yeah. Exactly.
Are we always considering it as a constraint? Is it always?
Yeah, I mean, I just come to that. Huh? So, I mean, given this basis, how do I go to SU2? In fact, exactly. So you just take some, let's say, A times sigma 3, SU2 Lie algebra, I mean the Lie algebra, A sigma 3 plus, say, Z sigma plus Z bar sigma minus, right? This will give you Hermitian matrices. But what if you have chosen another reality condition? Suppose you say that, no, I'm going to choose a reality condition like this. Of course, I mean, look at the full complexified Lie algebra, you should allow arbitrary complex numbers here, right? So it will be 3 complex dimensional space. But what we are doing is we are taking some, imposing some reality condition, right? So here we impose a reality condition that this is real and these two are complex conjugate of each other. But suppose you have chosen another reality condition. So we take just a real A sigma 3 plus B sigma plus C sigma minus. But these are all real. Everything is real. This will be a non-compact. And you can see that what Lie algebra is this. I mean, if you take SL2R group, SL2R group. So what is SL2R? It is it's a 2 by 2 matrices. The group is defined by 2 by 2 matrices whose determinant is equal to 1, right? With a real coefficients. So let me not use, something else. Let's call it A, B, C, D. If I take a 2 by 2 matrix, then the determinant condition is simply A, B minus B, C. So the determinant of this guy is A, B minus B, C, and we are setting that equal to 1. Okay. So that is, but this is of course non-compact. Why? Because I mean, you can arbitrarily increase, for example, suppose I fix B and C, right? I can arbitrarily increase B and A to all the way to infinity, right? I can still satisfy this condition. So it's non-compact. The parameter space is not bounded. It's non-compact. And this is exactly the Lie algebra of that. Because what will be the Lie algebra of this? If you write this guy as identity plus small A, B, C, D, but tracelessness condition tells you is minus A. That's exactly what you get from here. Right? So you see, by choosing a different reality condition, you're getting SL2R. But this is non-compact.
So we took different slices of
different slices, yeah, exactly. But from the point of view of the Lie algebra, you basically can learn everything from this SL2C. I mean, going to the complexification and then the way we are proceeding. You find the root space and so on. So you find, learn everything about the Lie algebra.
Another question about the Barnard exercises. One was about the algebra relation for SU2, but in an abstract way, you have only the commutation ratios.
Yes.
Then using this, you need to show that they must be Hermitian. Is this what follows, or is it something?
I don't know which one. Okay, I mean the Hermitian. Well, I mean, depends on what's your. I mean, if your generators satisfy TA, TB. I don't know.
It was I epsilon TC.
I epsilon, right? I mean, TA, TB, the commutator is going to be. Okay, so what we are saying, we are not sure whether this is Hermitian or anti-Hermitian, right? That's what we are saying, right? Okay, if it was whatever it is, whether these guys are Hermitian or anti-Hermitian, commutator is always going to be anti-Hermitian, right? I mean, that's clear because this is nothing else than TA TB minus TB TA. Okay. Now take the dagger of that. This will be TB dagger, TA dagger minus TA dagger, TB dagger. Okay. Now whether it's Hermitian or anti-Hermitian, the difference is just a sign, minus sign. But since I have a square of the minus, there will be always plus, right? So this is the same as TB, TA, whether T's are Hermitian or anti-Hermitian. Either way it's going to be the same. The first term and second term will be TA, TB, right? That's clear, right? Whether it's or the anti-Hermitian. So this becomes okay. This same as minus TATB, right? On the other hand, now here you have some structure constant. Let me just call it FABC. I don't know whether there's an I there or not, huh? And it's a TC. If I take the dagger of that, I'm going to get on this side. I'm going to get, after taking dagger, I will get F bar ABC. I mean complex conjugate of it, and TC dagger. But the left-hand side, the dagger on the left-hand side is just minus of the itself, right? So this is telling me this is nothing else but minus FABC TC. So we have this equality, and you see from this, I mean, if the F's were real, then TC must be anti-Hermitian, right? Whereas if epsilon, if F is pure imaginary, then the bar will give you a minus sign, this cancels, and you just get TC dagger equal to TC.
But how did we decide these are TB and TB are either Hermitian or anti-Hermitian? Isn't there any other possibility?
No, but in the SU2 case, this is what we are doing.
It's not SU2. It's not one of the assumptions. The algebra is the only assumption.
I see. No, then I don't see how you can conclude that. I mean, I think the one has in mind either choose Hermitian basis or anti-Hermitian basis. Otherwise, there's no particular.
Already choosing this algebra like this fixes the group as SU2. Is it enough to say?
Yeah, I mean, once you give me structure constant, the algebra is completely fixed. I mean, and the dimension, of course, it's three-dimensional in this case, and structure constant, that completely fixes. But if I give you some random algebra, I mean, I do not about SU to something general, then it is not immediately obvious, right? Hermitian or anti-Hermitian.
But can we say that, following the arguments, we have the commutation relations like I times epsilon,
Right.
F is like this.
Yes.
So this somewhat corresponds to SU2 because algebra fixes the type of the algebra. And for SU2 we have unitary matrices and the generators are therefore Hermitian.
Yeah, that is true. Yeah.
This is a
You can do that, yeah. But I'm saying that just if I just give you some generic structure constant, it's not obvious you can write it as the Hermitian or matrices and things like that. So it's not. Yeah. For SU2, I mean, given that once you define the structure constants, it's completely fixed. Algebra is fixed completely. I mean, of course, structure constants itself depends on the choice of basis. So even different structure constants might correspond to the same Lie algebra. Right? You can change the basis. So, but provided in some basis you can get back to epsilon ABC or I epsilon ABC, then it is SU2 algebra.
I have a question in section 7.6. I think because we did it but in a different way, maybe.
What is this?
Things of results.
This is what sorry, I don't have the specs. Is it with 3 bar? The SU2 or what are we discussing? SU2 or SU3 here?
I don't know. SU3, I guess. No, SU2. SU2, yeah. So, this goes SU2. So, yeah, and this one.
Oh, SU2 and SU3. Okay. Yeah, and then the question is what?
Did we make it like we didn't? I mean, did we cover it?
I mean, for SU2, we have covered completely generally, right? Spin J prime. This is okay, just spin half, right?
Okay.
But in general, we have seen if we take a J and J prime, then you'll get, and you want to decompose in terms of irreducible representation, you'll go from J plus J prime to J minus J prime.
In the same way that it's yielded here, or maybe, I guess, different notation, or...
I don't know. I mean, unfortunately, I cannot read. You have to tell me.
Why don't you?
I don't have the specs. I don't-
7.6 you say?
Huh?
Yeah, we did, I think it's, but we didn't use the same notation. We used the tensor notation.
I see. Yeah.
So instead of the saying plus 1/2 minus 1/2, we said Tij, which is 1 or 2. And we did that, I think.
I mean, the way we did, I don't know if it's the same way or not here, but the way we did was just to look at the spin j prime representation. So this, you know, plus j up to minus j, and here
we,
goes.
the multiplicity and
Exactly.
yeah, but
Which is, I think, should be
here
the-
is completely like this. I'm not sure, but it's there's nothing about the multiplicity or it's like
No, I mean, there should be two of states. I mean, spin half, this is talking about spin half, right?
That's only the
So
example.
it should be the same, right? You have a half state, you have a minus half state, and you have a half, minus half, and minus half, right? I don't know if this is the notation, I'm not sure.
Yes.
Huh? Okay, so the total spin, total J3 quantum number of these two is 0, right? Each of them. So the multiplicity here is 2. There are two states. I mean, this is J equal to 0. So if I write a total J, total, I don't know, J3 quantum number. So this is plus 1, minus 1, 0, 0. So this is what I meant. There are two of them, right? With a 0 and then one combination of these two guys together with this and that forms a spin 1 representation. Then the other combination gives you a spin 0 representation. So it's the same thing. Okay. Now let's, I think, so now we start going towards, okay. Okay, chapter 9. Chapter 9 is just a one-page chapter. So let me just, it's just some definition. So let me just say that. Okay, so this is chapter 9. It is just a bunch of definitions. Yeah, we already know. I mean, I think most of it we already know. We already have seen the definition of the Lie algebra. Right? The Lie algebra was, you have seen the definition, I've given the definition many times. Right? So first of all, you have some, so let's say G is first of all a vector space. What that vector space, you all know, it means that if I take any two elements, I can multiply, any element I can multiply by a number. And again, it's a number could be real or complex depending on whether it's a real vector space or a complex vector space. But if you multiply by a number, take any vector, multiply by a number, it's again inside this set. Or additions are also defined. I mean, if I take you two, give you two elements, some of them also exist. So there's a notion of addition. It's okay. That's a standard vector space. But then together with that, a Lie bracket is also there. Lie bracket has been defined. So x, for every x, y belonging to G, there is a antisymmetric object which is also in G. I mean, so this is equal to minus yx, it belongs to G. And this bracket preserves the vector space structure. So it is linear, basically, bilinear. Okay, that's what it means. Okay, in other words, if I have ax1 plus bx2, comma y, that's the same as ax1 y plus bx2 y. So it's linear. It's linear in the first argument and similarly linear in the second argument. Okay, that's what it means. And very importantly, that it satisfies the Jacobian unity. So the standard, I mean the Jacobian identity x1, x2, x3, plus the cyclic thing, right? x3, x1, x2, plus x2, x3, x1. Equal to 0, the Jacobian identity. So these are the three, these are the basic, that's the definition. So any G which satisfies this condition is called a linear algebra.
If they are already matrices, they already satisfy the
Yeah,
condition.
exactly.
But I don't know if it's right. If we have a matrix representation of a real algebra, we automatically satisfy all these conditions.
Yes.
So it is also be valid for any other possible representations that might not be matrices. Maybe derivatives.
That's yeah. I mean, for example, all this pointer algebra you can write in terms of derivatives, right? Rotation you can write as a x mu d by dx mu, that anti-symmetrized.
In that terminology, it's not obvious that they satisfy this, but
you have to check that. Yeah, you have to check that.
In this definition, you don't need the Lie algebra, the Lie group.
At the moment, you can just talk about the Lie algebra directly. Although our interest was that from the Lie groups, we looked at the infinitesimal version of the group, and then we found these relations. But otherwise, actually we didn't discuss these relations very much, but roughly I tried to give an intuitive argument why all these relations follow from the group. All these are coming from the group product itself, restricted to the infinitesimal. Right? But, okay. Yeah. Okay, so this was already done, and then we also discussed the notion of subalgebra. Okay, let's call it something else, some subalgebra, let's say H, subalgebra H of G. So somebody gives you this algebra G, and then I'm looking at some subalgebra which is contained in G. Okay, that is every element of H is contained inside G. Okay, and you have to. So first of all, H is a sub vector space of G. I mean, G is a vector space, and what we are saying is H is a subspace, sub-vector space. So in particular, if I take any two elements of H and I add them up, I should get back an element of H. I mean, surely it will be an element of G, because G satisfies that condition. But you need to make sure that it's also an element of H. Okay, so that's what it means. Or multiply by number, should again be back in H. Okay, and the level of algebra, if I have X and Y, which belong to H, so of course, if it belongs to H, obviously it belongs to also G, right? But then, if you take the Lie algebra, I mean the bracket, this bracket, the rule for this bracket is the one which you are using in G. Okay? When you define the G, you have defined what you mean by a bracket. Okay? You have to use the same concept, same notion of the bracket here. It's not some new concept of bracket. The same bracket structure. Maybe I can just put here G to indicate that it is the rules given in G. And that's contained in H.
When we say the rules, we mean the structure coefficient constants, right?
Structure constant, for example. Or, I mean, already we know that for every pair of xy in G, a commutator will be another element of G, right? Which let's call it Z. Then here also, the xy should be equal to Z. And all one is saying is that Z must actually belong to H. That's what one is saying. So this is the concept of subalgebra, and the example of this we have seen many examples. I mean, the SU2 case. In the SU2 case, we had the general element was given by xi sigma I, right? Xi is any real number, right? That's in the Hermitian. So this is an arbitrary Hermitian 2 by 2 matrices, but you can. So this is G. G is basically the elements of this type, where all the xi are in real numbers. That's the G with the standard commutation relation. They are now the matrices. So the standard commutation relation being the bracket. Now if I take the subalgebra H, I could choose a subalgebra to be simply H equal to just x sigma 3, for example. This is clearly subalgebra, right? Okay. Now a slightly more complicated example. If you can take the SU3 subalgebra, okay, and you can take SU3 subalgebra had all those 3x3 Hermitian matrices, traceless Hermitian matrices, right? So those were the three. And in one language, I mean, in the language that we have already introduced, this could be written as H1, H2, I mean, generated by a basis for the SU3. Basis for the SU3 you could take as H1, H2, and the roots, x alpha 1 plus minus x plus minus alpha 2, and x plus minus alpha 3. In the complexified basis, in the complexified SU3. Of course, you can go back to the real by putting some reality condition on the coefficients.
The real SU3 is also the real SU3 that we're talking about.
Yes.
Also a subalgebra of the complexified SU3, right?
Yeah, that's right. Yeah, correct. But I mean, now say let me just take the. Okay, I mean, what does it mean? It means that the conditions I'm going to use are basically if I take x alpha I some zi, then it should be zi bar x minus alpha. That will give you band SU3. Okay. So this will be the general combination will be this plus, let's say, x1 h1 plus x2 h2, where zi bar. So there are 3 complex numbers here and 2 real numbers. So that will be defined. That will be the SU3 slice. But now in this I can take the subalgebra. We saw there are several SU2 subalgebras, right? For every non-zero root. For every of this root, there was an SU2 subalgebra, correct? So, for example, if you take the SU2 subalgebra, which is simply say H1 and X alpha 1 and X plus minus alpha 1, 3 of them, okay? With again same reality conditions. I mean, so arbitrary element is X1 H1 plus say Z, Z1 X plus minus plus alpha 1. Plus Z1 bar x minus alpha 1. Okay. So this will give me one SU2 subalgebra. Right? And this is true for any, I mean, you choose another one, alpha 2, you can, again, that defines to be another SU2 subalgebra. Or if you choose x alpha 3, another SU2 subalgebra. So many SU2 subalgebras are there. Of course, the Cartan subalgebra is also a subalgebra, but it's a kind of a abelian subalgebra. Now here it's slightly more complicated because subalgebra is also non-abelian. So this is a, okay. Now there is, I mean, you have seen this several times, so that's why I'm going quickly, because this part you have seen in many different ways. So now, so what is the new concept here? The new concept in this chapter, and that's all. I mean, that is why it's just 1.5 pages, this page, this chapter. The new concept, which is actually very, very important, is what is called ideal. Or I prefer to call it, because ideal doesn't give me any meaning. I mean, you know, what is ideal? You say ideal situation, no? Situations are ideal. But I prefer to call it invariant subalgebra. There's another terminology. I mean, sometimes people use this, sometimes people use that. So invariant subalgebra. Okay. So there's another. So if let us suppose I have a G, original algebra, and some subalgebra H. H is a subalgebra. So H is contained in G, and the subalgebra. In the sense of all that definition, subalgebra. Then there's a special type of subalgebra which satisfies the following property. Suppose X belongs to H, and Y belongs to G. Y belongs to G. So arbitrary X belonging to H and an arbitrary Y belonging to G. This, of course, this may or may not be inside the H. I mean, this in general, any arbitrary element of G. Then, if it satisfies that the commutator of X and Y, okay, what can you say about this commutator of X and Y? Where will it be? It's certainly in G, right? Because if X is in H, obviously it means X is in G, right? and G is an algebra, so both these elements are in G, so certainly it belongs to G. This is generally true, right? But the special case is when this happens to be in H. Okay. Then you say that this is an ideal or an invariant subalgebra. Okay. That is the. Then H is called. If this is true, if for all x belonging to H and y belonging to G, x, y belongs to H, then H is called an ideal or invariant subalgebra. Invariant one understands, right? Because you see what it is saying is that the adjoint of action of the Lie group, the Lie algebra G, keeps the elements in H. It doesn't take you out of the H. So it's a kind of invariant subalgebra, invariant space for the adjoint action. No? So that's why I prefer this, because name itself tells you what it means. Whereas ideal doesn't tell me anything. Okay, so this is a very important concept. And although we will not be using very much, but I mean, just in once or twice I'll be using it. But the classification of general Lie algebra uses a lot this concept of ideals. But we will not be using too much of that.
Casimir element is also.
Sorry.
Casimir element.
No, Casimir is not an element of the Lie algebra, right? It's not. Casimir is not an element of the Lie algebra. Casimir is constructed. If you give me a representation of the Lie algebra, so now that you can think of it as matrices, these guys are matrices now, right?
Then we have multiplication.
Then you can multiply, yeah.
So Casimirs are also dependent on the representation.
Yeah, actually, in each reducible representation, Casimir is an identity operator, right? It's just a number times identity. And that number is what you usually, when we say Casimir, we usually mean that number. Like for SU2, J times J plus 1, that number. But it acts as an identity in each irreducible representation.
And it somehow states in which representation we are. If we know the Casimir.
Yeah, correct. Yeah, that's right. Yeah.
I guess if you take the Casimir and the zero vector as a group, it will be an ideal. I don't know, I'm not sure. But
no, take an example. Let's take SU2. Then what are you saying? I mean, what's the question?
if you take the Casimir operator and the zero vector as a group, as a subgroup of.
No, I mean, first of all, now we're talking about the Lie algebra, right? Not the group. At the level of Lie algebra. Casimir is not an element of the Lie algebra. That's what we are saying, right? Casimir is a product of two generators and then sum over all generators, right?
Yes.
But the product is not inside the Lie algebra. It's the commutator which is inside the Lie algebra. Okay. So example. Let's just give some examples. Then situation will become more clear. Take a simple case. Take the direct sum SU2. If you take the direct product group SU2 times U1. Or SU2. Take any group. G1 times G2. G1 times G2. Okay. Two groups. I'm taking direct product. So at the level of Lie algebra. So this is group. At the level of Lie algebra, it's a direct sum. It's a direct sum. Let's say G1 plus G2. And the elements, if x1 belongs, x1, x2 belong to, if x1 belongs to G1 and say x2 belongs to G2, then by definition, this x1, x2 is 0. That's the direct sum. The commutator of, so any element, any guy from here will commute with any other guy there. Okay. Then it's obvious that the commutator, only non-zero commutator would be when both elements are here, but then they are contained here, right? Or if both elements are here, they are contained here, then that satisfies the definition of ideal, right? So in fact, in this case, both are ideals. Both are ideals of the direct sum. But it's again a very trivial case.
We proved that direct sum and direct product relation when we are talking about tensors, right? The direct product of two groups
Yes.
corresponds to the direct sum of the algebras.
Yeah.
This,
At the level of infinitesimal, it's going to be.
yes, but to prove that the tensor transformations in the SU2 group is enough to prove that the relation is true. I mean, the infinitesimal V group element acts.
I mean, yeah, okay, this follows from simply the definition of this one, right? So if I take, so what is an element of this? The element of this will be sort of denoted by G and H, let's say. So G belongs to G1, H belongs to G2. Okay? And the product rule is defined as the following way. So if I add another element here, G prime, H prime, okay, then the product is simply G times G prime using the first group, the product rule of the first group, comma, H times H prime. So from this it immediately follows that the Lie algebra of this guy is not going to see the Lie algebra of the other guy. Because the product is just between them.
Yeah, then product turns into a sum at the infinitesimal level, then they won't see that.
They won't see that, exactly, that's the point. Yeah.
Can we consider if we have a Lie algebra and it has a center, an element inside the Lie algebra that commute with every element, can we consider it as a Casimir operator also?
I mean, not really. I mean, that's not Casimir operator. Yeah, I mean, if, for example, the U1 generator itself commutes with itself, right?
Mm-hmm.
So you can call it Casimir, but normally people don't use the word Casimir.
So there is a condition Casimir to be excluded from the Lie algebra.
No, I mean, so Casimir by definition is something which just commutes with everything in the Lie algebra, right? So if it's a U1 algebra, then the generator commutes with itself, right?
Mm-hmm.
But there, of course, what is the Casimir in that case? What is the representation of U1? U1 representations, irreducible representations, are always one-dimensional. Okay, so everything is one-dimensional in the U1 representation. So irreducible representations, and the only thing that labels the representation is the charge. You know, U1 electromagnetism charge. No, charge is what defines a representation. So charge is in fact precisely the way the U1 generator acts on the state. It is the eigenvalue. Okay. So in that case, Casimir is the generator itself. But that is a very trivial case where it just is an abelian algebra, right? We are really interested in situations which are not abelian.
Yeah, but inside non-abelian algebra, you can find that element that called center. That
yeah, but I'm not. I mean, in fact, we are going to eliminate all that. We are not going to include any of these things. Huh? We are not going to include. In fact, the interesting case. I mean, we are actually focusing on that situation where. So, I mean, I didn't. Let me just first give you examples of ideal. Then I'll come back to it. This ideal. I mean, I'm just trying to say that what we will go argue is that. I mean, from now on, we will exclude cases where there is an ideal, which is abelian. Okay. Mm-hmm. So this situation appears when you have abelian ideals. Okay. But if there is no abelian ideal, you will never have that situation. Yeah. So now let's see if. So now let me take. This was a very trivial example. Let's take a slightly more non-trivial example. Your famous Poincaré algebra, right? Poincaré algebra. Okay. So Poincaré algebra consists of the Poincaré, or of course it's the same as any Euclidean. Euclidean Lie algebra also the same. Euclidean transformations. It's the same. In Poincaré and the Euclidean difference, the only difference is that metric. Metric is indefinite. I mean, whether some signs are plus or minus, no? Whereas Euclidean everything is plus. That's the only difference. But the structure is essentially the same. Now Poincaré has two types of generators. One is what we call Lorentz transformations. Another is the translations. Right? There are two types of transformations in the Poincare. The Lorentz transformation, boost, and translations. Just straightforward translations, right? So let's call this generator, I don't know, lambda. There are of course many generators. The number of generators is 6, right? Altogether there are 6 of them, but let me just call them as lambda. And translation, I will call them as P mu. So this is lambda mu mu. This is anti-symmetric mu mu, that's why there are 6. And P mu. P mu is a translation. The generator of translation. Momentum generator of translation. Now if you look at the general structure of the Lie algebra, lambda with lambda, and I don't put any indices here, I mean they're arbitrary. I just want to look at this general structure. This is again of the form of some lambda, some combination of lambdas. Right? 2 Lorentz transformations, when you take the commutator, is again a Lorentz transformation. Right? That is, so I'm just writing schematically. Lorentz commutator of the Lorentz elements gives you again Lorentz element. P with P is 0. Right? The general structure, translation generator. I mean translation commute, right? You can translate from this direction or another direction and do opposite way. First you translate this way and then translate that way. You're going to get back the same point, right? So it commutes. Okay? But the interesting thing is lambda with P gives you again P. Okay, this should be, I mean, what I mean by that, this is not equality. I mean, there are, of course, there's a certain, if I apply a lambda mu nu on P nu, you're going to get some combinations, no? But all I mean is the commutator of a Lorentz with the translation gives you a translation. Okay, that's clear, right? Okay, if so, then the claim is that if you look at the Lie algebra, this is a sub Lie algebra. I mean, if you take just the translations, this is sub Lie algebra, and it is an ideal. You see, because you can see. First of all, if you look at this is certainly containing the Poincare, and P with P is 0. Okay, P with the lambda. Okay, so this is certainly a sub algebra. P with P is 0. But what is more important is that P with lambda is again P. But that's exactly the thing that we are saying, right? Take an element of H, take an element of G, commutator is again an H. No? So here that means a translation, so this means this subalgebra. So translational subalgebra. Algebra of the Poincare is an ideal.
And Lorentz boundary group is not Lorentz plus.
Yes, yeah. But, so Lorentz, this is also a subalgebra, but it is not an ideal. Because lambda with P, it gives you P, not lambda. No? So, and yeah, Lorentz is not an ideal.
But at the same time, they are not a direct sum of Lorentz and Lorentz.
Exactly. That's the point. That's the reason why this happens. Yeah. If it was a direct sum, both will be ideals. Yeah. Exactly. Okay. So this is more non-trivial. Okay, maybe this will become clearer. But so what we will do is, from now on, we will assume that the Lie algebra that we are considering has no abelian ideal. You see, this is not only an ideal, but it's also abelian, because this is an abelian algebra. Translation is an abelian algebra, right? So we have, this is an example where the algebra has an abelian ideal. So from now on, we'll be excluding that. Okay? We'll be excluding that. The algebras which do not have an abelian ideal are called semi-simple. This is what the definition. And we'll discuss it in more detail later. But I just at the moment mentioned that an algebra that has no abelian ideal called semi-simple. Semi-simple Lie algebra. This is the and yeah, that's what we'll be studying actually. And in fact, once you reduce here, then basically, I mean, you see, the point is that this may have ideals, but all we are saying is that the ideals are not abelian. So it may have non-abelian ideals. That's okay. That is there. But the only statement is that it doesn't have an abelian. Doesn't have an abelian idea. And then there is a definition of simple algebra. This is called semi. So you will obviously question what's a simple then, right? And the simple algebra is the one which has no ideals. Simple algebra is an algebra which has no proper meaning, there is always a algebra itself would be always an ideal, right? But when you say proper subalgebra, proper ideal, proper subalgebra means it's not the full algebra, it's smaller than that. Huh? Neither the full nor the trivial one, zero dimensional. No? It's somewhere in between. So there is no proper ideal. That's what I'm saying. And of course, it's not abelian itself. It's not U1 and is not U1. So you forget the U1, excluding U1, you have no other proper ideal. That's the definition of simple algebra. Now the point about this is that simple algebra, and there is a theorem, which I don't know whether we'll prove it or not, that any semi-simple Lie algebra can be written as a direct sum of simple algebras. So if you know everything about simple algebras, then you know everything about the semi-simple algebras, right? And the other thing is that in the situations where you have this abelian ideals, they are pretty much like this semi-direct sums. So you can that can be obtained as taking some semi-simple algebra, about which suppose you have learned everything by the end of this course. Okay, then you can take that and take a semi-direct sums with the abelian algebras. It's exactly like the Poincare. So this is why we are focusing on this part. If you understand this, then I think you understood a lot. Abelian algebras are trivial, right? It's these parts which are non-trivial. So this is why one is focusing on this. Semi-simple, and actually we'll be focusing on this. Because as we said, every semi-simple algebra can be written as direct sums of simple algebras. So you might as well just focus here and learn everything about that, then you know everything. All the semi-simple algebras also.
Did you just say that Poincare is semi-direct sum of semi-simple two algebras?
Yeah, no, it's not semi-simple. The semi-simple, by definition, will have no abelian algebras. Has no abelian idea, including itself. I mean, it's not. So semi-simple is not abelian. So here it's basically a direct sum of the Lorentz. I don't know how shall I call it. Semi-direct sum. Semi-direct sum. With R4. I mean R4, whatever the dimension is. The translation is just the R4, right, in four-dimensional space. So R4. So Lorentz plus, this is abelian, and this is an ideal. Yeah. Of the Poincare.
So I mean, is R4 semi-simple or simple?
R4 is abelian. So it's not semi-simple. Neither semi-simple or simple.
Because there are ideals which are not.
Yeah. Okay, so this is. I mean, we will soon. I mean, I will probably not today, but tomorrow we'll discuss. We'll introduce the notion of metric on the Lie algebra, and then you will see a big difference between the two cases. When you have a when you have an ideal, an abelian ideal, or when you don't have the abelian ideal. In one case, when you don't have abelian ideal, then this metering is non-degenerate, it's invertible. Okay? But if it has abelian ideal, then it is not invertible. The metric is degenerate. So you'll see a big difference between that. But for the moment, today, let me just complete. I will do that tomorrow, but I wanted to just quickly go through the 10th chapter. And 10th chapter, I will not do anything except one, because we have already done everything else. We have in detail done SUN. I mean, SUN in terms of what is the Lie algebra of SUN. No? Not in the level of the SU3, we studied all the roots and all these things, but we didn't do that. But at least we have a general definition of all the SUN Lie algebras, right? And similarly for SON, we have definition of the Lie algebras, right? But there is one class of algebra which we have never discussed, although I mentioned that in several times, but just in passing, I didn't discuss in any detail. And then we will move on to that. So far we have seen SUN Lie algebras. So this is a n cross n. I mean, this is basically the Lie algebra of n cross n traceless Hermitian matrices or anti-Hermitian matrices, depending on. Okay. SON was again n cross n antisymmetric matrices. The Lie algebra level. The group level is orthogonal or special orthogonal, but then the Lie algebra level it's antisymmetric. Okay. Now these algebras, as you can see, they are well defined for any n, right? So there is an infinite number of such algebras, right? N can be any integers, 2, 3, 4, 5, 100, million, whatever, right? And for each of them there is a Lie algebra. So this is what's called infinite series of Lie algebras. These are, okay, I will, so actually there's a classification, I am kind of, this we will see in the end, but there is something called a Dinkin classification of all Lie algebras, all simple Lie algebras. Okay. The series which is called AN, I'm just mentioning, don't think that I'm not explaining anything. So, okay, this is just a terminology, nothing more. We will come back to that towards the end. Bn, Cn, Dn. These are all infinite series. N can be anything. And these are nothing else but SUN plus 1. Okay. The reason why there's a shift is because in Dinkin classification, this number is a rank of the Lie algebra. Okay. And we have already seen SU3 has rank 2. SUN plus 1 has rank n. Okay. So this is the reason for the shift here. Bn is what we'll study that later. Is a 2n plus 1. This is SPn, and this is what I'm going to discuss today now. And these are SO2n. So there's a big difference between even and odd orthogonal. It will become clear by the end of this course that there's a big difference between them. That's why they're classified differently. This is a Dinkin classification. This is called Bn, Dn, and Cn is what is called symplectic. Okay. Now I want to focus on this here, okay, today, because you have already seen these guys. In the sense that you know what this Lie algebra are. No? These are traceless Hermitian. These are antisymmetric matrices, and then the algebra of that. And we have studied SU2, SU3 here in some detail. Right? In some detail we have studied. Okay, now we'll, this is the missing link, right? We have never seen the symplectic. So I just wanted to do that. Actually, we have seen it. We have seen it in the classical mechanics, right? In the classical mechanics, when if you remember, there's a way you can either formulate it in a Lagrangian way, using Lagrangians, equations of motion, or you can go to the momentum space. Or you can go to this Hamiltonian framework, right? where you introduce the canonical coordinates, okay, Q and P, right? And there was some, the Poisson bracket, you define a Poisson bracket, and these symplectic transformations are just the transformations in the phase space. So let me just write it, maybe it's become clear. So remember in the classical mechanics, you have seen, let's say I have some coordinates Qi, some configuration variables Qi. Then for each of them, you have a conjugate momentum, right? So these are the configuration variables, and these are the momentum. So think of a particle moving in some space. Q's are the positions, the position of the particle in some I being the dimension of the space in which it is moving, right? And Pi are the momentum. And then, you know, as usual, okay, and then what do they have? There is a Poisson bracket structure, Poisson bracket. Structure, which basically just says Qi, Pj, Poisson bracket. This I specify, I put here PB, the Poisson bracket is delta I, is delta ij, and I mean it depends on the convention. And the opposite one with the Pi Qj is minus delta ij. This is how we define symplectic, the Poisson bracket. More explicitly, what it means that if I give you two functions on these variables. So let's suppose this I goes from 1 up to n. Then this is n variables and this is n variables. So we have phase space is 2n dimensional. Okay. These are the coordinates of the phase space. So phase space is 2n dimensional, of which n of them are the coordinates, configuration variables, and n are the momentum variables. Now, if I give you some, some two functions, let's say some function f of q and p, all the qi's. I mean, by this I mean all the qi's, all the q's and all the p's. And another function g of q and p. Then you define the Poisson bracket fg. Poisson bracket is nothing else but, let me keep the same convention of the sign. It's not here. I just want to keep the same sign. It is. It's just. It's basically f df over dpi dg over dq I, and minus other way around, df over dqi dg over dpi summed over I. Here's a Poisson bracket. I mean, maybe there could be a mismatch between overall minus sign in these signs. It doesn't matter. That's not important. I mean, overall sign is not important. That's not. It's okay. So okay. So this is how you define the Poisson bracket. And you know, this Poisson bracket is used to define the equations of motion. You know, you construct first of all the Hamiltonian. Hamiltonian is a particular function on the phase space, and you define, say, q dot is nothing else but h, the Poisson bracket between Hamiltonian and the q. And similarly for the p dot, the Poisson bracket between h and p. This is the one way of attacking the classical problem, classical physics, right? Instead of the Lagrangian formulation, you have this Hamiltonian formulation. Anyway, so this was one of the crucial elements in the whole discussion of the phase space formulation. Okay. Now, what are these symplectic transformations? You see, symplectic transformations are the ones that when you, by the way, you can see that if you, maybe there's an overall minus sign here, I'm not sure, between this relation and that relation. Maybe this is minus and that's plus, okay, I don't know. But we can check that. Take the f to be simply just a qi, and g to be pj, let's say. Huh? Okay, a particular function, qi and pj. Then you apply that, this guy drops out, because df by dp is only qi. This one gives me, so this is now, so let's say f is qk, and g is pl, let's say. Then the only time you'll get contribution is when I is k, and then it gives you 1. And then I here should be also L, right? So therefore, this just gives me, this result will just give me minus delta KL, right? I mean, you have a sum, right? The summation over I. But this tells me that since f is qk, the only time this will give you non-zero is when I is equal to k. And that is 1. dqk divided by dqi is delta ik. So this will be delta ik, first term, minus here. And then this one is pl, dpl by dpi is delta il, right? Right? And then I have to sum over I, but when I sum over I, I'll just get that. Minus delta k. So this is just generalization of that. I mean, this was for specific functions, but here it's now for arbitrary functions. Okay. Now, what is the canonical? What is the symplectic transformations? Symplectic transformations are the ones which leaves this Poisson bracket invariant. So in other words, maybe you take Q and P, go to some Q prime and P prime, some new variables. But in such a way that with respect to Q prime, P prime, again the Poisson bracket is simply minus delta I. You see, the Poisson bracket remains invariant. Just like, I mean, this is like when you say the orthogonal transformations, it is something which does not change the inner product of two vectors, right? The inner product of two vectors. Here, instead of inner product, it is a Poisson bracket. The Poisson bracket doesn't change. That's what we are saying. So that is what. So this is the same as QIPT. Doesn't change. That's what it's saying. Huh? Okay. That's the definition. Okay.
Maybe from the common sense, it's like if I can make a rotation for the coordinate, I can make a translation, and I can, for example, also change the coordinate from Cartesian, for example, to spherical, and all of those transformations keep the bracket the same.
Well, it's not, because, okay, you can do that, but then you have to also transform the momentum suitably.
Mm-hmm.
For example, if you go to the radial coordinate, then you have to also go to the radial momentum. So there are some transformations which you need to make. Yeah. But I mean, it's not just that. I mean, you can just talk about, okay, yeah, I mean, this is a definition of symplectic transformation. Anything which satisfies this, any transformations which satisfy this condition, then this is called symplectic. More generally, in terms of the functions, you see this Poisson bracket I can write in a somewhat convenient way, in the following way. So let's go back here and try to see this Poisson bracket. I can, so this is how we define the Poisson bracket, right? I mean, we can rewrite this Poisson bracket by introducing some notation. Where shall I write it? Maybe here. This is just a notation. It's nothing. It's just a convenient notation. Otherwise, it's nothing more than that. I can write this FG Poisson bracket is equal to. I will define now what is it. F hat transpose E G hat. Where what is G hat and F hat? F hat is basically df over dp1, df over dp2, all the way up to df over dpn, and then continues df over dq1, etc., all the way up to df over dqn. Okay. So basically, when your hat is nothing else but you apply this operator, d by dp1. So you're just applying this operator, d by dp1, d by dp2, all the way up to d by dpn, and then d by dq1, all the way up to d by dqn. Okay. So this operator acting on some function. So if this acts on f, I just call it f hat. There's an abbreviation. Because in this definition is the derivatives which appear here, right? That's why I'm introducing this notation. Okay. So this is f hat and similarly g hat. Now f hat transpose will make this is a column vector. F hat transpose will make it a row vector. And what is E? E is exactly this block matrix. So this is everything is a 2n dimensional vector, right? So this is a 2n row vector. That's a n column vector. 2n. Why? Because there are n of the p derivatives and n of the q derivatives. Total is 2n, right? So this E has to be a 2n by 2n matrix. Okay? So this is 1 cross 2n, right? Because it is a row vector. Has to be 2n cross 2n. This guy, and this guy is 2n cross 1. So this is going to be a number, right? After using the matrix multiplication, it is the number. And this E has a structure 0, 0, identity, and minus identity. This is n cross n identity. So this is n by n blocks. This 2n by 2n I have written in terms of n by n blocks. So this is summarizing this formula. This is the same formula, nothing different, same formula, but written like this. Okay. Now, so what we want to do is we want to make some transformation. So the question is, what kind of a transformations will leave this invariant? So the idea is to take some transformation, I call it G, let's say G. G, this is a 2n by 2n matrix. Right? Everything is acting on a 2n dimensional vector. So there's a 2n by 2n matrix, which satisfies this property that G transpose E is this matrix, G is equal to E. Consider such matrices which satisfy this condition. If you have such a matrix, then you see you can make this transformation. So what shall I call? I mean this guy, let's call it D, this operator D. This is a derivative operator. And so you just make this transformation, D goes to GD. G goes to GD. So you can see it will give you some linear combination of these derivatives, right? But that's exactly like when you make the coordinate transformations, when you take the derivative, you have to use a chain rule to find what is the derivative with respect to the new coordinates, right? So this is what I'm saying, D goes to GD, then you'll find that this F hat, E, G hat, F hat transpose, G hat, goes to F, F hat T, then you have a D transpose, E, D, G. Right, it's clear, right? I mean, because if you look at the F hat transpose, it is the same thing. I mean, you have to take the transpose of this guy, right?
You mean G transpose, not D transpose? D is a transformation matrix.
Sorry, G. D, exactly, you're right, right. Yeah, this is G transpose. G and G transpose, exactly. Right. Yeah. But then that will be the same. If the G satisfies this condition, you see that the Poisson bracket doesn't change. Okay. That's this is just a way of writing it. I mean, what I have started telling you before was the coordinate transformation. Q and P goes to some Q prime and P prime. If that happens, then of course you can also ask what happens to d by dq and d by dp. It can be written in terms of, it will become d by dq prime and d by dp primes, but they can be rewritten in terms of by using the, what is it called? What is it called? Jacobian. Is it called Jacobian? No, not Jacobian. Huh? Yeah, just the standard. I mean, d by, if I make some transformations of the coordinates, let's say xi goes to some xi prime, then d by dxi prime, so xi prime is some function of xi, fi of x. Then I will write d by dxi prime by the chain rule, using, is the same as d by dxj, d by dxj, or right, d by dx, I can write it as xj prime, d by dxi, right, the chain rule. Yeah. And then you get this things, yeah, this is dfi, or dfj or dxi. This is now a function of x, so the derivative makes sense. And this is the matrix. This gives you the matrix, this matrix elements, G. Now this x involves both q and p. I mean, this is some, say, k dimensional. The I goes from 1 to k. Then what we have, this is k by k matrix, right? Because this has two indices, I and k. So you can rewrite this. This guy is d by dxi is some mij d by dxj prime, where mij is nothing else but that. So that is what I'm doing. The G is basically that. Except now we have a 2n dimensional space. Phase space is 2n dimensional. Okay. So that's what I'm doing. So this is the so this is a definition of symplectic transformation, symplectic group. So at the level of infinitesimal algebra, we can infinitesimal transformations. So G, this little g, then so at the level of infinitesimal transformations. Is this here? I just erased that one part, but I just want to keep this. Is a 2n by 2n in block form, 0, 0, identity, n cross n, identity, minus identity, n cross n, right? This is the E. So if I look at this equation and write it in the infinitesimal version, so I will get here identity plus, let's say G is equal to 1 plus m transpose, m is an infinitesimal. So I just look at the first order. So G transpose becomes m transpose, then E 1 plus m is equal to E. And that tells me that m transpose E plus, so that is, if you take the first order, we want to look at the first order. So this times that times 1, or 1 times this times that, right? So plus E m is equal to 0. So that's a condition of the infinitesimal level. Now this is, you see, so this I can rewrite this as EM transpose is equal to EM. This equation, right? Because I can take this on the, I can take this on the other side. So EM is equal to minus M transpose E, right? But if you take the transpose of this, what is this? This is nothing else but M transpose E transpose. But E is an antisymmetric matrix. So E transpose is minus. So this is the same. This equation is the same as that equation. Okay. So that means E times M is a symmetric matrix. That's what. So it's completely different from the orthogonal SO case, right? In the SO case, it was not this. In the SO case, again, there was an equation which was like this equation, except that instead of this E, it was an identity. Or more generally, if I choose some different coordinate system, it may not be identity. But the important thing is that it will be a symmetric matrix. Metric is a symmetric matrix, right? So you're going to have a G transpose symmetric matrix times G is equal to the same symmetric matrix. So this is very different. In orthogonal case, you have a symmetric matrix here. In the symplectic case, you have an anti-symmetric matrix in this. I mean, in this equation, G transpose E, G is equal to E. This E is anti-symmetric. That's a big difference between symplectic and orthogonal. Okay. So this is the thing.
Lorentz group is also called orthogonal, right?
Yeah, I mean, it would be, but it's a, I mean, it's yeah, it's orthogonal, but not exactly orthogonal with the eta, right?
Yeah.
That is, because orthogonal group will be compact.
Yes, it's the compactness change, but
Compactness.
the eta and symmetry of the eta is also there,
Exactly.
and all the arguments follow.
Exactly. So it's a symmetric matrix again. Yeah. Eta is 1, 1, 1, minus 1, or other way around, no? But whatever it is diagonal, so it's obviously symmetric matrix. So these are all, yeah, all of these Lorentz groups, etc., are like orthogonal,
Is this E, can it also be called as a metric on base space?
Well,
It's
this
not
you
a
wouldn't,
metric.
no, metric, it's not metric. I mean, it's not, because I mean, for the metric, if I give you some Q and P, and I want to give a Q prime and P prime, I want to look at the inner product. That would be the metric,
Yeah,
right?
but Poisson bracket behaves like an inner product.
No, I mean,
It's not, for example.
yeah, I mean, okay, maybe, but I mean, yeah. Because the inner product, I mean, all the metric, all the notion of inner product is very much linked to the symmetry. It's always symmetric. Either symmetric or Hermitian, depending on whether it's complex or real. So, yeah, here this is different. I mean, this okay, this appears in this naturally in classical mechanics. Huh? I mean, very long before any group theories were known, there was already classical mechanics and Hamiltonian formulation.
Does E and M commute?
Sorry?
Does E and M commute?
Does what commute? Sorry?
E and M.
No, I mean, no, not necessarily, right? No, I'm saying this is a definite. So M, whatever it is, has to satisfy this condition. Okay. So now let's just, since you asked this question, let's look at it in a slightly more detail. So let's say, since everything is being written in this block form, so let's write also this M in the block form. Let's suppose I write M is equal to A, B, C, D in this block form. So each of them is n by n, n by n, n by n, matrix. Then this equation becomes M transpose becomes A transpose, C transpose, B transpose, D transpose, right? This is M transpose. And then E is 0, identity, minus identity, 0. And here you get, for others, the term EM is 0, identity, minus identity, 0. And then you have A, B, C, D. That's equal to 0, 0, 0, 0, right? That's the equation. So we can open it up and see what kind of equations we get. So we get, let's multiply this first term. So you get here minus C transpose, right? That's the first term here. Then this with that gives me A transpose. And this with this gives me minus D transpose. And that one gives me B transpose. That's the first term. And this term, it gives me plus 0 to 1. So C and D, and minus A and minus B. Okay. So if I, and this is supposed to be equal to 0, 0, 0, 0. That's the equation. So it immediately tells me that C transpose equal to C. So this implies the following relations. And B transpose equal to B.
To to see the first one.
Yeah, sorry?
The first equation, it's that's,
Because this is supposed to be equal to 0, 0, right?
yeah, I mean, it's equal to C, not 0.
I'm sorry. Yeah. C transpose equal to C. Thanks. B transpose equal to, and then A transpose equal to minus D, right? That is from here. From here, you'll get the same equation, right? Because the transpose of this equation gives you that. So these are the three equations, and you can count how many parameters are there, because this one, C is an arbitrary n by n matrix, but it has to be symmetric. Because this equation tells me C is symmetric, so there are half n times n plus 1 parameters here, and similarly here half n times n plus 1 parameters. And A is an D is an arbitrary matrix, right? Arbitrary n by n matrix. For whatever choice of D, you just take AT equal to minus D, right? So there are n square parameters here. So total number of parameters is 2n square plus n, which is n times 2n plus 1. That's the number of parameters. Yes. So this Lie algebra is that much dimensional, n times 2n plus 1 dimensional. Which is the same, this counting is the same here, you see. What we are saying is that if I take any, if I take this matrix E times M, it's any symmetric matrix, right? But once I take any symmetric matrix, then I can write, so M, this equation tells me that M is E inverse times any symmetric matrix. Any symmetric matrix, right? That this equation already told you. Now, any symmetric 2n by 2n matrix, how many will be there? So this is a 2n by 2n symmetric matrix. So it is 2n times 2n plus 1 divided by 2, which is the same number, right? I mean, of course it had to be, otherwise there will be something. Otherwise we would have made a mistake somewhere. Okay, so this is the symplectic. Now, of course, this kind of this group is not compact. This group is not compact. Right? For example, let's see. I mean, already. I mean, take a simple example. I mean, take just n equal to 1. Okay, n equal to 1 at the level of group. I mean, to look at that compactness, non-compactness, you should go back to the group, right? So at the level of group, we had. Let's say G is some A, suppose G is A, B, C, D. Okay. And we have the condition G transpose E, G is equal to E, right? So if you write that A, so you get A, C, B, D, and E is 0, 1, minus 1, 0, and G is again A, B, C, D. This is supposed to be equal to 0, 1, minus 1, 0. That is at the level of, I'm just taking a simple example, n equal to 1. Otherwise it becomes very long matrices to multiply. To see whether it's, okay, so now if I just open this up. So here the left hand side, further multiply first this one here. We have AC, BD times 0, 1, C, D, minus A, minus B. Left hand side, I multiply this thing. So you see this guy is 0, AC minus CA is 0, so here it is 0. This one gives you AD minus BC. This one gives you BC minus AD, and that one is 0. And that's supposed to be equal to 0, 1, minus 1, 0. This is the equation. So you just have one condition, AD minus BC equal to 1. So just the determinant equal to 1, that's all. Okay. But this is the same as SL2R. We saw SL2R is exactly that, right? And that was non-compact. And you can see it's non-compact because, I mean, if I fix this B and C, I can arbitrarily increase B and A as large as I wish. And I can always find a solution. I mean, I can arbitrarily increase B, then I can solve for A, which will also be very large, right? unbounded. There's no bound. Okay, so it's non-compact. In particle physics, since we are always, apart from the Poincare, apart from the group which acts in the space-time, that is of course non-compact. But the groups that act on the internal symmetry of the internal symmetries of the particles and so on, the internal degrees of freedom, those we always take them to be compact. Okay? Because frankly, we don't even know how to deal with the non-compact internal symmetry groups. We don't know how to write a unitary theory on them, right? So we'll be always using compact groups. There you may say that, well, symplectic groups will never appear, so we don't have to study symplectic group. But that's not quite true, because there is, just like SL2 had a compact version, which was SU2. Remember the way we did that? Once you complexify the Lie algebra, it depends on how you take the real section, no? Reality condition. In one reality condition you got SL2, another reality condition you got SU2, right? Same way, you can take this as SP as symplectic group. These are denoted by SPN. This group is called SPN. SP just means symplectic, short form for symplectic, and N. Unfortunately, there's a confusion here, because in some of the books they will call it SPN, and some of the books they will call it SP2N, and this is a big source of confusion. And there is a reason for both of them. 2N because it's all 2N by 2N matrix. Right? We're talking about the defining equations are all dealing with 2N by 2N matrices. But SPN is also because N is a dimension of the configuration space. No? So I prefer this usually, and I think also in this notes always this notation is used, because it will turn out that the rank is N. Okay? The rank will be N, not 2N. It will be N. In any case, whenever you take some book and you see that they are writing SPN or SP, first thing you should ask, what is their convention? You know, because different books use different conventions, so you have to be careful. Okay, so the point is that there is just like as I said, SL2R, and SU2, they are just starting from the complex Lie algebra. You can either go to SL2R or SU2 depending on the reality condition. Okay. The same way it turns out, even though SPN, the way it appeared in the classical mechanics, they were non-compact. That's how the classical mechanics appeared, right? But then you go to the Lie algebra, complexify the Lie algebra, and then go up to something which is compact. And the way to do this is actually very simple. Well, not very simple. At least one can say it in very simple way. So far we talked about SPN or SP2N, depending on your taste, R, right? Because all these entries that were inside this G were real. Classical mechanics, of course, you would do that because all the Q's and P's are real. So obviously you're not going to mix Q and make Q and P complex. That is clear. But you may imagine that instead of that, I take SP and complex. So all the coefficients are complex. They will satisfy the same equation. Okay. But G, now the G is a 2n cross 2n matrix with complex entries. We don't put any restriction that should be real. And then you define what we call, I don't know, the notation, the sort of, let's say, the compact version of SP, compact version of SPN as the intersection of SPNC with SU2N. So you look at SU2N, these are all 2n by 2n matrices, right? So you can define an SU2N group or SU2N Lie algebra, right? Same way SPN, C, we already have these relations, except that we allow these guys to be complex now, A, B, C, D, to be complex. Okay. So now you take this is a group or a Lie algebra, that's a group or a Lie algebra. I mean, group or Lie algebra, infinitesimal or versus finite element, and you just take the intersections of them. And that is what usually when you see in particle physics, symplectic group, they mean that. Sometimes it's called USPN, unitary, USPN, to clearly distinguish that this is the compact version.
Like you do the SP1, and you show it to be isomorphic, can we say that? I don't know. To SL to R.
Yeah, so in that case you'll take SP1C, which will be the same as SL2C, because the only condition was that AD minus. I mean, you see here I didn't use so much. I didn't use the fact that it is real or complex. No, this AD BC could be complex, right? Because the equation is just that. There is no complex conjugation here. G transpose. No, if it was complex conjugation, then you have to be careful. No? But there's no complex conjugation in this equation. So this ADBC could be complex. So you just take SL2C. Okay. So you take this ABCD, which is complex, which satisfies this condition. But that condition is simply determinant equal to 1, right? But you're taking this to be complex. Now take that and the intersection of that with the SU2. Actually, you could say U2, right? It doesn't matter. In fact, you could have equally well called it intersection of U2N. It doesn't matter. Because determinant is 1 anyway for this matrix. So you don't need to worry about that. Yeah? So it's the same as U2N or SU2N. So now you just, the intersection just means you just take those elements A, B, C, D, which also happen to be inside SU2N, SU2. But so in that case, it's simply SU2, nothing else. Because symplectic thing just gave a condition of determinant equal to 1. But that's anywhere part of SU2 condition, SU2 condition.
Is it useful to do this to understand symplectic group? After the intersection, all we end up is SU2 itself again? Can we
in this particular case, I mean, that's because for n equal to 1, but that's not the case for a higher n. So for the higher n, yeah, I mean, you see already from dimension formula, this is not the dimension of SUN, right? It's not. So it's not. It's just an accident for n equal to 2. It's the same. There are some accidents that happen. Maybe I just mentioned that briefly, but this is not generally true.
Well, we can use it to understand symplectic group in terms of compact groups.
Yeah, correct. Yeah, I mean, at the level of Lie algebra, because anyway, the Lie algebra, you anyway work with the complex. So the Lie algebra of this guy, USPN or SPN, they are all the same. The level of complexified Lie algebra is all the same. So you can learn some properties from that. Yeah, there are some coincidences, we saw SU2 is the same as SP1. I mean USP1 to be more precise, the compact version of SP1. Yeah, I mean then you will see some kind of coincidences. For example, the dimensions. If I just write down dimensions of various groups, SUN, the dimension is n squared minus 1, right? That is the dimension that we already seen. Dimension of SON is n times n minus 1 by 2. And SPN, in our notation SPN, that is 2n by 2n matrices, that is n times n plus 1 by 2. N times 2n plus 1. N times 2n plus 1. That is SPN. Now you can see that we already saw for n equal SU2 and SP1 have the same dimension. We already saw, right? And we also understand, and that's what we discussed just now. N equal to 2 is, this is 3, and n equal to 1 here is 1 times 3, so 3. Both are 3-dimensional. And in this case, and you see that just by dimension you cannot conclude the two things are the same. Because as a vector space they will be the same, right? Because any two vector space with a given same dimension, they are isomorphic, no difference. But here we have a bracket also. The bracket is not guaranteed that two brackets will be isomorphic. But here it turns out to be exactly the same. The bracket structure is also the same. Now take another thing. If you take, let's say, let's say SO4. Okay. Well, that dimension is 4 times 3 by 2, which is 6, right? But that's the same dimension as SU2 times SU2. I mean, at the level of group or at the level of Lie algebra SU2, direct sum SU2. Okay. It's the same. And it happens that at the level of Lie algebra, this is exactly the same as SO4 Lie algebra. It happens to be the same, exactly the same. But at the level of group, just like SO3 and SU2 had the same algebra, right? But at the level of group, we saw it was not exactly the same, right?
They may not be exactly the same, but at the level of SO2 and SO3 and SU2, we had a double couple.
Yeah. That's
Are
right.
they always
Also,
such maps between when the vector spaces dimensions match, but the groups don't match? Can we always find a map?
no, I mean, it will be always at the level of some global issue, not at the local. Because the exponentiation of these guys will give you the same elements, right? So all the elements which are, I mean, it's only some global structure could be different. Okay, like happens in SU2 and SO3. What happened? The two elements of SU2 were mapped to the same element. Same thing happens here. This SO4, SU2 cross SU2 is a double cover of SO4. Two elements here are mapped to the same element. Since local structure will not be that different because infinitesimal things will just exponential map will take care of the local.
But if the local dimensions match, we can always find a global map between the.
Yeah, by exponentiation, and in some cases, if it's not connected, like O3, you can never find the -1 by exponentiation. That will not happen because it's disconnected. But elements which are connected to identity, yeah, that you can reach. Okay, that's one thing. This probably we'll see maybe in more detail later. But no, I'm not sure. But then there are another thing which is. Let's take, if you take SO n equal to 5, SO5, and let me see, actually even simpler one first. Take SO6. Its dimension is 6 times 5 by 2, 15, right? So the dimension is 15. And take SU4. There's also a dimension 15. 4 square minus 1. And again, it turns out to be Lie algebra is same. Okay. The group level again is a double cover. SU4 will be double cover of SO6. Okay. But at the level of Lie algebra is the same. And then finally, if you look at this one, SP2, which has dimension 5, right? Is it 5? No, sorry, 2 times 5, 10, right? This is 2 times 5, so that is 10, dimension is 10. And the SO5, this also has dimension 10. Okay. And again, these two algebras are isomorphic algebras. But the group level, again, this is a double cover of SO5. So there are a lot of such questions, but generally, so this happens for small n. No? This happens for some very special small values of n. But the moment n becomes large, this n of this this n, SUN, SON, SPN, then they are not. Even if the dimensions match. For example, you can see the coincidence here that if you take SO2n plus 1, it is always a dimension of SPN. I mean, you can see this for any n. If you look at the dimension of SO2n plus 1, which is what? Just apply the formula. So you get here 2n plus 1 times 2n plus 1 minus 1 by 2, which is the same as n times 2n plus 1. Right? So it's the same as SPN dimension. But this is that's not true. That the algebra is only for this case, only for n equal to 2. These two algebras are isomorphic.
To be sure, we need to look at commutation relations.
Yeah, precisely. Yeah. And we will see it. I mean, I think hopefully we'll see it that we will find that the roots are different for the two things. And once the roots are different, then clearly, the algebras are not the same. Yeah, we will find that. Hopefully, we will try. the roots are different. So. I mean, roots are the kind of the good way of kind of this root system, basically which is decomposing in terms of eigenstates or the Cartan. That's a good way to kind of think of the Lie algebras in general. And also from physics point of view, because when you say something is in the representation, so these different Cartan generators you call different spins, I spin or Y spin or U spin or various names, and the quantum numbers of these are exactly the what we call roots or weights. All right, so I think I already exceeded too much. Late. So this was one thing which was missing, and from tomorrow we'll go into more the general discussion. Any questions?